Hi everyone. So here we go with the last lesson of Unit 3. And the name of this lesson is actually called, it's Lesson 10, Percentage Yield. But before we do the lesson, I wanted to just spend a moment. I thought of something yesterday that might help some of you to visualize what's happening with these limiting and excess reactants that we talked about yesterday. And so I'm going to return to a little example I did yesterday. We did this one in the lesson, and if you need to refresh yourself on that, you can look at yesterday's lesson. But essentially, it's a chemical reaction where you have two reactants, and you're wondering which one is limiting and which one is excess. And we did this yesterday. You had 60 grams of this first one and 50 grams of this second one. So what we did was we calculated the number of moles. We converted them both to moles by using the molar mass of each of those reactants. And then finally, we divided by their coefficient. So we divided by the 6 in this case and the 4 in this case. And once we did that, we determined that the nitrogen monoxide was limiting. Okay, so we came to that conclusion. But I just wanted to show you visually what is happening, and I thought that this might help some of you. And so if we visualize the nitrogen monoxide as being this bar, and we visualize the C3H6 as being this bar over here, and so and I'm showing this bar as being slightly higher because we have more moles of it. So look at this. We have 1.67 moles of this and 1.43 moles of this. And just out of interest sake, notice that for the reactants, we have 0 of all of those. So no moles, no moles, and no moles there at the beginning of the reaction. Well, we let the chemicals start reacting, and what's going to happen is that the amounts of the reactants are going to start falling. Okay, so I'm just going to show you this. So sure enough, this bar starts falling. Now it doesn't fall as quickly because look, 4 of these get used up and 6 of these get used up. So that bar starts falling, and so does this bar start falling. So look at this. This bar shows the amount that you have, and so there you go. It's falling, it's falling, it's falling, and in the meantime, it's falling faster than this one. But at the same time, these bars over here are growing. So you can picture in your mind that those bars are starting to grow, okay? Basically, as you start making the products. Okay, so this bar is growing. Sure enough, this bar is growing. And sure enough, this bar is growing. And again, we can imagine that, that this bar, this last one, this nitrogen, is growing at a slightly lower rate because there's only one of them being produced. And this water one is growing at the fastest because there are 6 of them being produced. And for the first product, it's in between those two. Well, just to finish this analogy or finish this discussion, is you can imagine then that eventually, because this nitrogen monoxide is limiting, eventually it runs out. So it kind of goes to nothing. Okay, and so this one is, and I'll just eliminate it, it's gone. It disappears. Because eventually, because it's limiting, eventually when it gets to 0 and the reaction stops. Well, the other reactant continued to fall, but eventually when the nitrogen monoxide runs out, it stops because the reaction stopped. And so it stops with some amount left over. So at the very end of this reaction, you still have some mass of this one left. So this is the excess reactant, but so you have a little bit of it left. This one is the limiting reactant, so you have 0 of it left, and obviously you will have produced some amount of these products, some amount of these products, and some amount of these products. But you've got, this is what would be left in the reaction vessel when you're done. All of one of the reactants is gone because it was limiting. Okay, so I just thought maybe that might help some of you to visualize what was happening. Okay, well, today we're moving on to this last lesson, like I said, and it's called percentage yield. And we're going to start by defining a few terms here. The first term I'm going to define is called theoretical yield. And theoretical yield is the amount of product predicted to form on the basis of the balanced chemical reaction or equation. So this is really what we've been doing up until now. We use stoichiometry. So I'm just going to write this. We use our stoichiometry steps, and we predict how much will be made. But just bear in mind that that's theoretically how much will be made. It's also the maximum amount. If everything went perfectly, we would make the theoretical yield. But as you're going to see, you rarely do make the theoretical yield. So the actual yield is the amount that of product obtained in the reaction. So if you actually went into the lab and did the reaction, you'd actually get, this is the actual amount you would get. And then we have this other term called the percent yield, which is a comparison. It shows the efficiency of the reaction by comparing the theoretical yield to the actual yield. And we have a formula for it. So what the formula is the basically you take the actual yield that you got in the lab, you divide it by the theoretical yield that you calculated using stoichiometry, and multiply it by 100, and you get your percentage yield. And so you could imagine that if in fact you had a reaction where you had an actual yield of 10 grams from the reaction, but before you did the reaction, you did the stoichiometry, and the stoichiometry said that you were supposed to get 20 grams. Okay, so when you divide those two, you would say that you have a 50% yield. Okay, so all right, that's percent yield. Let's do an analogy here. I've been using analogies a lot in this unit, and I think it's nice to picture things. Well, let's do an analogy that involves chocolate chip cookies. So here is the recipe, and as you will see by my recipe, I'm not a very good cook, but let's say that you combined 2 cups of flour with 3 cups of sugar, 1.5 cups of butter, and 1 cup of chocolate chips. You mix them all together, and according to the recipe, you should make 24 chocolate chip cookies from this recipe. Well, let's say I did all this. I got together and I was really hungry, so I mixed all these ingredients, mixed them up into a bowl, and started baking. I baked all afternoon, and at the end of the day, my actual number of cookies produced, the actual number of cookies that Mr. Webster made was 20. Okay, so the 24 cookies that the recipe told me I was going to make was theoretical. Okay, that's what the recipe suggests is the theoretical yield. The 20 is the actual yield. Okay, so my percent yield from my day of cooking would be 20 divided by 24 times 100 equals, okay, 20 divided by 24 times 100, and I got an 83% yield. Okay, well, why? Why would that be? A lot of you have cooked before. Why don't you get your theoretical yield? Well, in cooking, there's some really good reasons. Number one, usually there are some preparation issues, I'll call them, of making the cookies. And so I've given you a few examples. One is probably there's some leftover cookie dough in the bowl after you're done, and you probably scrape it and eat it. Okay, and that's fine, that's good. Number two, you may be cooking with a friend, and when you turn your back, they scoop into the batter and steal some of the cookie dough batter and decide they're going to eat it. So that reduces your yield. Maybe unfortunately you burnt a few cookies and so you threw them in the garbage, and so that would reduce your yield. These are typical reasons why you don't get the theoretical yield. I listed one other issue, I think. Yeah, let's say that theoretical yield is based on making a standard size of cookie, and let's say you didn't make all the cookies the same size. Maybe you made some of them bigger, and so that clearly that may limit your yield. Now, it could also increase your yield if you made them all really tiny, but basically it's a reason why you don't get the theoretical yield. Okay, so that's the analogy. Let's go back to chemistry now. And I pulled this question out from yesterday's lesson just so it would give us something to work with. And so this is one we did in yesterday, and it said if you had 120 grams of each of your reactants, so there you go, we did it 120 and 120. Eventually it says how much of the HNO3 are you going to make? Well, let's say that this question said, when you did this reaction with the 100 and the 120, you actually made 50 grams of HNO3. So notice that they've got to give you that extra piece of information. I wrote it up here just to show you. So there's, in these questions, they tell you this one extra piece of information. Let's say you actually made 50 grams of the HNO3, and then they said to you, what's the percentage yield? They said that's your new question. Well, you'd have to still go through and do everything you did yesterday. And so I want to show you, here are the 4 steps of stoichiometry where we can, determine which one was limiting. So we did that. We determined that the hydrogen peroxide was limiting. So we used that 3.53. We did our mole ratio. We figured out that we needed, we would produce 1 mole of the HNO3, and then we came up here and we got this. Now remember, using stoichiometry, you actually are calculating a theoretical yield. Okay, so we now need to compare this to what the question said you actually got. And so you would finish this question off by saying, well, the percentage yield for this one is 50 divided by 63 times 100, and you would do that new calculation, 50 divided by 63 times 100, and you get a roughly 79% yield. Okay, so that's all that would change. Everything is the same as we did yesterday in the lesson, except that they'll give you this one little extra piece of information. What is the actual, if you actually made this, what's the percentage yield? Okay, well, before we do another sample question, I'll walk you through the whole thing. Why is this? It's in baking, we came up with some reasons, but those don't necessarily apply to chemistry. It's not like someone's going to eat your batter in chemistry. So why don't you get 100% yield? Well, here we've broken it into 2. First of all, it may be an experimental procedure issue. So maybe some of the reactants were splattering as you were heating it, so you lost a little bit of the reactants. Maybe you spilled some of the reactants when you were filtering or transferring them. Okay. Other issues, maybe some of the reactants were impure. It said that they were, let's say a pure salt, pure NaCl, but there were some impurities in it, and so that the mass isn't completely accurate. Maybe there were some side reactions that took place, like as the reaction vessel started reacting, maybe there were some other things that were happening there that you didn't anticipate. And finally, maybe there were some environmental conditions that prevent the reaction from going to completion. In other words, maybe the pressure in the vessel increases too much and doesn't allow all of the reaction to occur, or maybe it's not warm enough for all the reaction to occur. So that there are good reasons why you won't get 100% yield in chemistry. All right, let's do one more question here. Here it is. We'll do this as a complete question. So it says barium sulfate forms as a precipitate in the following reaction. When 35 grams of barium nitrate is reacted with excess Na2SO4 sodium sulfate, 29.8 grams of barium sulfate is recovered by the chemist. Calculate the theoretical yield and then calculate the percentage yield. Okay. This is a classic question. So I want you to notice that it's not a limiting reactant question because we've been told that we've got excess of the other reactants, so we don't have to worry about it. So that's kind of nice. We don't have to do that extra step. But let's start by using stoichiometry to calculate the theoretical yield. So this is going to be the 4 steps of stoichiometry that we've been practicing. So step number 1 is to write the chemical equation, which thankfully we've been given here. So barium nitrate plus sodium sulfate produces barium sulfate plus 2 sodium nitrates. Okay, so that's the reaction. We're not done step number 1 until we write down what we've been given. So it says when 35 grams of the barium nitrate, so I'm going to, my little m is 35 grams. That's how much I've been given. It says, well, the theoretical yield of barium sulfate. So I want to calculate, my question mark will be how much of the barium sulfate do I make? Now, you got to be careful here. And I want to highlight this just for a minute. Notice that it tells you that you actually get this amount. Sometimes students will make a mistake in that they'll say to themselves, well, I should be writing that mass down here, and I'll actually do what they, so oftentimes students will write here the 29.8 grams, and they'll be confused as to, well, what am I solving for? But I want you guys to see that that's the actual yield. That 28 grams is what is the actual yield. And so we're going to need that as we calculate the percentage yield in part B, but it's not the theoretical yield. So I am going to get rid of that. Sometimes what I do suggest to students, because they like writing it down, is I write it up here. I write it above. The mass here is 29.8 grams, and I'll just write actual beside it. So sometimes I write it up there in my step number 1. Okay, so I'll check that off. We've done step number 1. Okay, step number 2 of stoichiometry is to convert everything to moles. And so the only thing I have to convert to moles is the barium nitrate. So I go N is equal to, it's little m over big M. That's my way of converting mass to moles. So it's 35 divided by, and I'm going to go and calculate my molar. All right, so here we go. I calculated my molar mass of barium nitrate. I just want to show you here. I did for barium, there's one of them. So I did 1 times 137.33. I got these numbers off my periodic table. Plus, there are 2 nitrogens, so 2 times 14.01. Plus, there's 6 oxygens. Remember, it's 2 times 3. The 2 in the brackets applies to both the oxygen and the nitrogen. So you end up getting 261.35 grams per mole. Okay, so here we go. We'll go back here, and we will put in here 261.35, and I'll divide those, 35 divided by 261.35, and I get 0.134 approximately moles. Okay, step number 2 is done. Step number 3 of stoichiometry is to do a ratio. So the ratio of barium nitrate to barium sulfate. That's what I'm trying to go from this reactant to that product. So here we go. It's a 1-to-1 ratio, which is obviously a nice one. So look, it's 0.134 to X. That's my unknown. Well, obviously, in a 1-to-1, the number of moles is just the same. So finally then, my step number 4 is to convert back to whatever I need. So my mass here is little n times big M. So it's the 0.134 that I just calculated times the molar mass of barium sulfate. So here we go. I'm going to go calculate that. So I calculated the molar mass of barium sulfate right here. I get 233.4. So I'm ready to finish this off now, finish part A off. So I'll put in 233.4. And when I multiply times 0.134, I make 31.3 grams. Okay, so that is my theoretical yield. So I've done part A. I just used my 4 steps of stoichiometry. So part B says to calculate the percentage yield. So here we go, part B. Well, the formula for percentage yield is the actual yield divided by the theoretical yield. The theoretical yield times 100. So here we go. The actual yield that they told me in the question was 29.8 grams. 29.8 grams divided by my theoretical yield, 31.3 grams, that stoichiometry told me I should have produced. And so in this case, 29.8 divided by 31.3, and I get a 95% yield. So that's how we do these questions. Give this a try, and I'll do a few homework questions and post them, and we're done the unit. So good luck, you guys, and let me know if you have any questions.